Alright, there's a diagram here of a DC electric motor. 50 turns of wire, that means 50 coils, 50 loops. Permanent magnets, north and south, provide magnetic field B of 0.3 Tesla, and there's a commutator, and this is the commutator here. And the first question is, explain the role of the commutator in the operation of the motor, 3 marks. Okay, the reason we have a commutator is because if we didn't have a commutator and this was the way the current went all the time, we can work out the forces on that using the right hand slap, and I'm going to do that very quickly. I think it's a downwards force on this side. You do the same thing, the current goes around and out this side. On LM you'd find there's an upwards force. This would turn over, but when JK got to the other side, it would turn over this way. JK got to the other side, there'd still be a downwards force on JK, and so JK would go back again. We'd get to here, it would go back again, and back again, and back again, and back again, and back again. So without the commutator, the coil will just oscillate. So the commutator, the main thing with the commutator is the commutator allows for continuous rotation. It does this by, now what that happens with the commutator is as the coil rotates around, the commutator rotates around as well, and each of the splits, as they go right around, the split here is touching Y here, but as it goes around to the other side it ends up touching X, so it touches the other side of the where the electricity is coming from. So it does this, the commutator reverses the direction of the current in the coil. Reversing the direction of the current in the coil every half cycle. And for our last dot point, 3 marks, 3 dot points. We're going to say this provides for the forces that only contribute to continuous rotation. Our next question is asking us, there's current I flowing through. When the coil is in the position shown, draw an arrow on side JK to show the direction of the force. Alright, so the field lines are going from north to south. And the current's going along this. If this is like a 3D picture, it looks like the current's going sort of into the page. This is, we want to know a force, this is our right hand slap rule. Now the way I'm going to position my right hand is this way. So if you had your right hand, you'd be positioning it the same way. I'm actually going to do it a bit more. Where that into the page there is the current on your thumb. The field lines go with your fingers. And this is the top of my fingers, this is my fingernails, and so that my palm of my hand's on the other side, which goes down. It's a downwards force on this guy. Let me just load the last file. Alright, so there's a current of 6 amps in the 50 turn coil. The length of the side is this. Calculate the magnitude, which means size, of the force acting on it. This is the formula F equals N bill. Now N is how many loops we have, B from the previous page, B was equal to I think 0.3 Tesla. I, here we have I, the current, and L, .05 meters, not 5 centimeters. Well, it is 5 centimeters, we're going to put it into meters, so that's what it is. So 50 times 0.3 times I6 times 0.05, and that equals 4.5 newtons. 4.5 newtons, there we are. I just copied and pasted this picture so you could just check here the magnetic field. Here it is here, as B, which is what I had here and what I've put in here to get the right answer.